The planet Pluto, situated at the farthest reaches of our planetary system, is surrounded by an enormous number of cold, wonderful bodies and asteroids within the Kuiper Belt, a colossal area of space beyond Neptune. Once regarded as the 10th planet, Pluto gets its name from the Roman god of the underworld. However, at a pivotal junction in astronomical history in 2006, Pluto was reclassified from its planetary status, reflecting the growing awareness of our solar system and the vast neighborhood we inhabit. Our ongoing excitement for the planetary system reflects a collection of distinct parts, different space rocks, a select group of minor planets, and a record of just 8 recognized planets. Throughout humankind's history of exploration, many eons of observation and study have led to significant advancements in our understanding. We have gained insights into their compositions, behaviors, and potential for supporting life, which illustrate our vast cosmic environment. Yet, amidst our growing knowledge, the allure of our own world continues to invite further examination and discovery. The James Webb Space Telescope, a pinnacle of modern cosmic progress, stands poised to uncover some of these mysteries, including those related to Pluto. Despite its modest size and irregular orbit, Pluto has held a special place in the hearts of many for years, marking the boundary of being the smallest celestial body in our solar system. Pluto's reclassification sparked a strong public reaction, highlighting the deep emotional connection people felt toward this distant body. However, practical concerns were raised about what qualifies as a planet. To maintain planetary status, an object must meet 3 criteria: orbiting the Sun, having sufficient mass to assume a nearly round shape under its gravity, and clearing its orbit of debris. Pluto ultimately failed to meet these criteria, primarily due to its irregular orbital path. The term planet has undergone an intriguing evolution throughout astronomical history. Initially, it referred to any large celestial body, including moons and asteroids. Pluto's discovery in 1930 by American astronomer Clyde Tombaugh stirred widespread excitement, only to be followed by the discovery of similarly sized objects within its neighborhood, raising questions about its planetary status. Amidst this discussion, Professor Mike Brown's 2005 discovery of a Kuiper Belt object roughly similar in size to Pluto further complicated matters, challenging the traditional definition of a planet. This led to heated debates within the scientific community, culminating in Pluto's reclassification as a dwarf planet during the International Astronomical Union (IAU) meeting in Prague in 2006. Thus, Pluto's transition from planetary status to a dwarf planet serves as a demonstration of the evolving nature of scientific understanding and the ongoing quest for clarity in the vast expanse of the universe. Following extensive discussions, a revised definition of a planet was proposed and put to a vote at the IAU meeting in August 2006. This new definition included both Pluto and the object now known as Eris, signaling a departure from the traditional notion of what a planet is and reflecting a more nuanced understanding of celestial objects. Eris, formerly known as 2003 UB313 and nicknamed Xena, was named after the Greek goddess of strife, reflecting the controversies surrounding its classification. Mike Brown, a planetary scientist at Caltech whose work contributed to Pluto's reclassification, gained widespread attention for his efforts and earned the nickname Pluto Killer on social media. This reclassification prompted a swift revision of educational materials, including standards and textbooks, to reflect the new understanding of Pluto and Eris as dwarf planets. However, not all members of the scientific community immediately embraced the IAU's definition. Some planetary scientists, particularly those focused on Pluto and similar objects, expressed concerns about the new criteria, leading to ongoing debates within planetary science. These discussions extended beyond the scientific community into the broader public sphere, raising questions about the accuracy of classification systems and the implications of renaming long-established astronomical terms. Despite these debates, the scientific quest to understand Pluto continued. In 2015, NASA's New Horizons spacecraft conducted a historic flyby of Pluto, delivering groundbreaking data about this distant world. The mission revealed a geologically dynamic planetoid with features such as nitrogen ice plains and a distinctive heart-shaped region that captivated the public's imagination. As we ponder these discoveries, it becomes clear that our understanding of the outer solar system and its constituent bodies continues to evolve. The reclassification of Pluto and Eris as dwarf planets marks a milestone in our ongoing exploration of the universe, highlighting the complexity and diversity of worlds beyond Earth. As New Horizons traveled through space at an astonishing speed of 32,300 miles per hour, it captured detailed images of Pluto's near side during its closest approach. However, due to the spacecraft's trajectory and the position of the Sun, Pluto's far side, often referred to as the dark side, remained hidden from view. Scientists carefully analyzed images taken by the spacecraft before its encounter to gather insights into this mysterious region. Despite the limitations of these images, they provided an exceptional level of detail, allowing scientists to discern surface features down to around 1 mile in size. This clarity far exceeded previous observations, including those made by the Hubble Space Telescope, which orbits Earth. The analysis of these images has provided new insights into Pluto's dynamic nature, with scientists investigating features such as the potential for a subsurface ocean and surface processes. Subsequent revelations, such as the presence of ammonia on Pluto's surface and the discovery of methane ice deposits, continue to unveil the intricate makeup of this world. Richard Binzel, a planetary scientist involved in the New Horizons mission, described Pluto as the gift that keeps on giving as it continues to surprise scientists with its volatility. Before the New Horizons mission, the best images of Pluto came from the Hubble Space Telescope, which showed a world with distinct surface features. However, New Horizons provided the first close-up views of Pluto's terrain, including the striking heart-shaped region and the immense frozen plain known as Sputnik Planitia. The discovery of Sputnik Planitia's unique layout, alongside Pluto's largest moon, Charon, has sparked interest in its geological composition, with some scientists speculating that it could contain a subsurface ocean that influences its surface features. The detection of ammonia in the ice covering Sputnik Planitia suggests active geological processes beneath the surface, indicating a dynamic and evolving world. As scientists continue to analyze the data collected by New Horizons, they are uncovering more clues about Pluto's complex and dynamic nature, broadening the scope for future exploration. The very terrain on Pluto's far side, including mountains, valleys, and plains, bears striking similarities to features seen on other celestial bodies with subsurface oceans. While the far side of Pluto remains somewhat obscured, scientists eagerly await future missions for closer examination. These anomalies fuel theories about Pluto's geological history and the role of its subsurface ocean in shaping its surface. These discoveries challenge traditional interpretations of planetary development and highlight the importance of distant worlds like Pluto. As New Horizons continued its mission, scientists speculated about the fate of Pluto's interior. Radioactive decay within its core may have generated enough heat to cause surface distortions, potentially leading to wrinkles or fractures similar to those seen on Earth. However, when New Horizons captured images of Pluto's far side, it revealed faults rather than wrinkles. Pluto's surface appears to have partially frozen over the eons, with a massive rift running along its near side, resembling Earth's East African rift system, likely a result of the freezing and expansion of a subsurface ocean. The age of this rift suggests that the ocean cooled rapidly after reaching the surface, possibly creating conditions suitable for the development of life. Additionally, the reddish tint of Pluto's surface, indicative of organic molecules, suggests the presence of complex organic compounds. Laboratory experiments have shown that such compounds can form through radiation, such as from the solar wind or cosmic rays, shedding light on the possible processes behind their presence on Pluto. The discovery of ammonia-bound ice on Pluto's near side supports the idea that the dwarf planet could harbor rich organic compounds. While this does not necessarily imply the presence of life, it suggests that conditions could support life if they were right. Measurements from Pluto's far side have not only confirmed the mission's success, but also led to the discovery of fascinating geological features, including towering ice formations. These structures, distributed across Pluto's surface, present a compelling mystery. Spectral measurements reveal that they are composed of methane ice, forming a belt around Pluto's equator. However, their origin remains uncertain, with hypotheses ranging from atmospheric freezing to degradation by intense sunlight. Understanding Pluto's cold environment and terrain requires careful analysis of its atmospheric conditions. Researchers are refining climate models to better replicate observed inconsistencies and intend to improve our understanding of this distant world. Researchers are refining climate models to better replicate observed inconsistencies and intend to enhance our understanding of this distant world. Despite Pluto's remoteness and the challenges of studying such a far-flung object, these new discoveries, driven by missions like New Horizons, highlight the immense potential for further revelations about its nature. In particular, scientists are working to develop a more accurate picture of Pluto's atmosphere, its icy surface features, and the possible interactions between its surface and subsurface layers. The varied topography of Pluto, including its massive mountain ranges, plains of nitrogen ice, and the strange rift valleys, continues to challenge existing models of planetary geology. While these features are reminiscent of processes seen on Earth and other moons with subsurface oceans, their unique characteristics suggest that Pluto's geological history may be quite different from anything we've encountered in our own solar system. Researchers are particularly interested in how the presence of liquid water, possibly beneath the icy surface, could have shaped Pluto's present-day landscape. The mystery of whether this liquid water could harbor any form of life remains unsolved, but the potential remains tantalizing. One of the most intriguing aspects of Pluto's surface is the discovery of methane ice and nitrogen-rich ice sheets. These icy features are not only fascinating because of their beauty, but also because they hint at processes that might be crucial to understanding the dwarf planet's geophysical activity. For instance, the large nitrogen ice plains on Pluto's surface may be a reflection of an active or evolving cryogeological cycle. These frozen expanses are subject to complex atmospheric and geological forces, which could help explain the diverse surface features and the possibility of subsurface reservoirs of liquid. With each new study and each new mission, our understanding of Pluto continues to deepen. The next frontier in the exploration of Pluto and the Kuiper Belt may involve sending additional spacecraft to investigate this region more closely. The technology required to explore these far-off worlds is improving at a rapid pace, with instruments designed to capture high-resolution images, analyze surface composition, and gather data on atmospheric and environmental conditions in increasingly sophisticated ways. Ultimately, the story of Pluto's reclassification from planet to dwarf planet serves as a metaphor for how science continuously evolves, influenced by new discoveries, technological advances, and shifts in understanding. As we learn more about Pluto and its neighbors in the Kuiper Belt, we are not just rewriting a textbook definition of what constitutes a planet. We are uncovering deeper truths about the very processes that shape the cosmos. With each new breakthrough, we move closer to understanding not only the origins and evolution of our own solar system, but also the potential for life in the most unexpected corners of the universe.